Okay, section 10.7, systems of inequalities. Last video for this week. Maybe the second to last video this week. I don't know. We'll see what happens. Okay, 10.7, systems of inequalities. What is an example of a linear inequality in two variables? Here's an example of one, y less than x. Linear, two variables, inequality. Okay, here's another one. Y less than or equal to 2x plus 7. There's another one. Linear, inequality, two variables. Here's another one. 1/2 x minus 6y is greater than root 2. There's another linear inequality in two variables. And generally, here is a system of linear inequalities in two variables. The coefficient on x, coefficient on y, we generally like to write them in this form when we're dealing with inequalities. All a, b, and c are all real numbers. A graph of a linear inequality in two variables is the set of all ordered pairs, that's G, ordered pairs that make the inequality true. Just like with any other equation, sometimes we say it satisfies the inequality, just like we say it satisfies the equation. So here's some examples of graphs of inequalities. You'll notice that half planes are shaded here. So in figure 2, the graph of y less than 2x, so the dashed line is y equal to 2x, and then all the ordered pairs that are in the shaded pink region, red, pink, I don't know, all of those ordered pairs still make the equation true. So for example, when x is 5, we have, and y is 0, 0 is less than 2 times 5. That's true, so that point definitely gets shaded. Same story over here with figure 3, y less than x squared. The dashed line is the parabola y equals x squared, and then we shade one side of the parabola on which those points satisfy that inequality. In figure 4, the solid line is y equals x squared, and then in this case we're shading the other side of the parabola because those are the points that will satisfy this inequality. So, your turn. Why don't you try graphing this inequality? Pause the video, give it a shot. Welcome back. Here's how I did it. Standard form is kind of annoying, so I put it in slope-intercept form. So in slope-intercept form, y-intercept is 6. Slope is 2/3, so I could rise 2/3 and run 3, or alternatively, because I don't have any room in my graph, I could rise negative 2/3 and run rise negative 2 and run negative 3. And that'll make my life a little easier. That gives me a second point here. And this is less than, not less than and equals to, so the line y equals 2/3 x to the 6 is going to be a dashed line because we don't want to include those points in our graph. Those points on the line y equals 2/3 x plus 6 do not satisfy the inequality y less than 2/3 x plus 6. And then we got to figure out what side of the graph to shade. So the way I normally do that is I pick a convenient point, and if that point satisfies the inequality, then I shade that side of the line. If that point does not satisfy the inequality, then I shade the other side of the line. So I'm going to pick 0, 0. So 2/3, 0 plus 6 equals 6 and 2/3. which is greater than 0. So that does not satisfy the inequality. That does satisfy the inequality. Yes, definitely satisfies the inequality. 0, 0. We get 6 2/3 on one side of the inequality, 0 on the other side, so we're good. So all of this stuff over here gets shaded. And that's how we graph a linear inequality. I glossed over something. What was it? The thing that I glossed over is I only picked one point on the side of the line and then shaded the whole other side of the line. So to prove that you shade the whole side, if one point satisfies the inequality on one side of the line, then everything on that side of the line satisfies the inequality, is involved. That's an involved proof, so we're not going to do it. But you just have to pick one point on the side of the line, see if it satisfies the inequality. If it does, shade that side. If it doesn't, shade the other side. I usually pick 0, 0 because the arithmetic's easier. So a solution to a system of linear inequalities in two variables is all x, y that satisfy all the equations. Not equations, they're inequalities. What are you talking about, equations? Inequalities. So let's try this. Graph this system of inequalities. Y less than or equal to x squared plus y squared less than or equal to 1. So if you want to give it a shot beforehand, go ahead and pause the video now. Give it a shot. Just sketching it together, we have y less than or equal to x squared, so I'm going to graph that first. It's generally what? We got this guy, 2 and 4, 2 and 4. It's just a parabola, right? And the parabola is included as a solution to the system, so we're going to do a solid line. Solid line for the parabola. Okay, what side do we shade? Well, I can't pick 0, 0 because I know 0, 0 is on the line. How about 0, 1? Yeah, 0, 1. For 0, 1, for the first inequality, that does not satisfy because 0 is not bigger than 1. So we shade the side that doesn't have 0, 1. So we shade this side over here, this side of the parabola. Now the other inequality, excuse me, let's use a different color. The other inequality, well, it's a circle centered at the origin with radius 1. So it's kind of like this. And then do we shade the inside or the outside? Well, we want all points, when we add their squares together, it's less than 1. So that is definitely the inside of the circle. If you're not sure about that, plug in 0, 0. 0 squared plus 0 squared is 0. That's definitely less than 1. So we're going to shade the inside of the circle. And then the solution to the system is the overlap. It's where the shaded region of each equation intersect. So it's going to be this region. I'm going to outline it in black here. This region, all in here. Those are all the points that satisfy both of the inequalities. There's some useful terms to describe these crazy regions we get when we graph inequalities. A vertex is a point where two adjacent boundary sides meet. So, for example, this point right here, so the boundaries meet, that's going to be a vertex. That guy's a vertex. Convex is a region is convex if we pick any 2 points in the region, we connect a line segment between those 2 points. If that whole line segment is in the region's convex. So just looking at the black region, if I pick this point here and this point here and connect them, the whole line segment doesn't lie in the region. So that region is not convex. It's got a little, goes in a little bit on the top. So it's a little concave, though that's not a technical term. It's not a convex region. Though this region in blue, the blue region, that would be a convex region. And a bounded region is bounded if there exists some circle that contains the whole region. So if there's hard boundaries, if the region doesn't go off into infinity, then it's bounded. We already looked at the vertices of the shaded region. Is it convex? We already discussed that. And is it bounded? Yeah, the black region is definitely bounded. I can draw a circle around it. You're going to make me do it, aren't you? Let's draw a circle. Okay, look. I drew a circle around the black region. It's definitely bounded. That is a messy graph now. I think that is all. Thanks so much for your time and attention. Good luck.